Yes.
Okay, then the recording is on, so we can start.
Okay. Oh, okay. Okay, very good. Okay, let's start then with the last lecture with the survivors here. Okay, first of all, I want to just, well, the general aim of this lecture was first to just let's say display or explain the various various features of black holes in anti-de Sitter, particular how they can be used to model phase transitions in the dual field theory. We have seen some examples of this. We have seen that black holes can model, for instance, the liquid gas phase transition in the dual field theory. They exhibit a similar first order phase transition if you lower the charge below a certain threshold. And they can also be used to model some sort of confinement-deconfinement phase transition. This is how the original Hawking page phase transition was interpreted. And so one can use black holes to learn something about the thermodynamics of the dual field theory. People have done this, and we'll see also another example like in this lecture. But also, on the other hand, you can use the dual field theory to learn something about black holes. So in general, for all these supergravity solutions, the preserved supersymmetry, you can count states, at least not for all of them but so far, but I mean, for a large part, we are able to, we have under control the microstate counting that one can do by counting ground states in the dual field theory. Also with other sort of corrections, for instance, higher derivative corrections and so on and so forth. So today I want to focus my attention on explaining. So we have seen that there exist black holes with various different horizons, like spherical horizon, also hyperbolic or homogeneous horizon. But I want to focus on making a comparison between which kind of solutions are there in Minkowski space, the preserved supersymmetry, and which other kind of solutions can expect to have in anti-de Sitter space, and whether they can have what are their supersymmetry properties. And in particular, I will focus on black hole solution, which have some sort of exotic horizon. What I mean with this is black holes which are either multi-center or other composite objects, for instance, like black Saturn. So black Saturn is really like it's formed by having a spherical black hole surrounded by a ring. And this can happen, there are configurations like this in 5-dimensional flat space. They can preserve supersymmetry, or there are also solutions of just with a ring, the shape, the horizon is shaped like a ring, let's say, in 5D. And so I wanted to make a parallel between what happens in flat space and what can, if we have some reasons to expect that some configuration can be there also in in anti-de Sitter space with respect to what they are there in flat space, let's say. So first of all, I'm gonna start. I'm gonna give you more like a status update based also on some work that I did with my collaborators and some work that appeared fairly recently. So I won't write too many formulas this time because I think that yesterday we also had a pretty technical one, but pretty technical lecture. But at least I hope I'm gonna give you a bit of the gist of the solution. But let me then just recap. So we have already seen multi-center black holes. Let me just recap how is the solution. So just to refresh your memory, because I think we have seen that probably in the second class, but just, so the first solution that was found by Jundra. Petro. This solution describes multiple black holes, in particular n black holes, with charge q, qi, and each one has the mass mi equal to the charge. And they are described by this solution, in which this is just the area element in just like flat space. And this is written in so-called isotropic coordinate, and they are supported, of course, also by a gauge field. So these correspond to solutions with the same mass and charge, that actually they can stay in equilibrium among each other because the gravitational interaction, the gravitational force is balanced by the electromagnetic repulsion. And as I was mentioning last time, these solutions also are at 0 temperature. They are extremal, and like zooming in into each one of the well, this one is actually the coordinates of the horizon of each black hole. You find an ADS2 times S2 throat. And these solutions are the first found in theories of like Einstein-Maxwell, or in so-called minimal supergravity. But also when you add scalars, like multi-center solutions were found, for instance, by Frederick Teneff and collaborators. Well, first by him, and then also they were generalized, or actually found analytically by him and another like student, I think, but the first paper was his. And so this is solutions with, let's say, solutions with scalars. And multiple charges. This solution has the property that basically you can displace the centers, you can put them wherever you want, provided that the mass and the charges of the black hole like rebalance. What?
Usually the horizon is a codimension 1 surface, but here if we fix all 3 xi's, what's the dimensionality of the horizon? Is it just family?
It's still an S2, each one of them. Now this is just like, I mean, you along each center you can put there some sort of like spherical coordinates. It's normal.
It just looks like if we fix x, the whole vector x to be the vector xi.
Yes.
To be at the particular horizon, then we are going to codimension 3.
Well, but close to the xi, I mean, just imagine you're close to xi, you just define the radius as radius minus, like the difference, I mean, you can just reparameterize, and close to that is really equal to a Reisenauer black hole. We can try to do the coordinate change at some point if you want.
I think you have to fix x to be only equal to 1 to the xi. So
yeah, exactly. You can use this.
all the x with only xi, so x to 1 or not?
Yeah, but it's still a whole vector, right?
Yes, but if you focus on just one center, you can put yourself in a coordinate such that you have only one component of xi, right? At least locally close to just one of the centers. And then the other you can just use them as two-dimensional, like the horizon, right?
One way to see it, so it's not manifest in these coordinates, but there's a coordinate singularity at the location of the center. So you need to choose symplectic coordinates. So that's always choose radial, spherical poles, and then you'll have one over r squared in the Helmholtz function. But on the sphere, you'll have r squared d angle squared, which is a solid angle squared. They'll cancel, and then you'll have the cube for the individual center times the solid angle squared, just like with the and so you had a coordinate change in maybe lecture 1 or 2.
Yeah, the coordinate change that like passes from the Reisenauer to the near horizon geometry.
Right, so the original r is just translated. So the original r equals q plus the radius and the distance. In these coordinates, you can go to negative radius.
Yeah, so in order to have a complete spacetime, you have to extend this thing. But there were papers about it. Like if you look for Hawking, and I think the title is something with like something like space-time with many black holes. I think you get but yes, in principle you can choose just one component for this, and then the other, and then you can change the coordinates, and the section of the horizon you'll see that it's proportional to qi, where like the area is qi squared, and then the section is just a sphere, to sphere. So yes, these are just so these are solutions. They're defined by solving the equations of general relativity, and it's one of the few examples that displays linearity, like in which the Einstein's equation displays linearity, because we can add as many centers, and we can also place at the coordinates that we want. By the scalars, at least this kind of like flat direction is partially lifted at least, and you have a rigid system, meaning given the charge, you have a specific distance between the centers that is fixed. So these solutions here and the counterpart found by Denef in Calabi-Yau compactifications, like preserve supersymmetry, at least a subset of them that you have, like that display this multi-center behavior, and they can also, like, their entropy was reproduced by microstate counting in flat space, and moreover, also in some parts of the moduli space, you have that these solutions are actually entropically dominant. So if you want, there is a nice essay by Denef and Moore, 07. This is an essay written for the Gravity Association, the association that gives a prize every year, and it's actually like a very nice, not super technical paper. Like, it's very short also. But so for our discussion about black holes in Anticythera, we would like to know, so these solutions also explain some interesting mathematics for what concerns microstate counting, and also they preserve supersymmetry. So given the fact that there was a lot of development in this microstate counting and the entropy matching, we would like to know if solutions like this can also exist in asymptotically ADS space. However, this is not quite. This turned out to be a very tough question, meaning that solutions like the linearity that is displayed by the Einstein's equation in asymptotically flat space is lost when you add a cosmological constant. And moreover, if you try to massage the equations of supergravity, try to solve the PPS equations with answers for multiple centers, turns out to be something very, very difficult. So to this point, no analytic or exact or numerical or like solution of multi-center black hole are known in anti-de Sitter space. However, like, of course, so you might think that indeed this is just like the solutions are there because there is a careful cancellation between the mass and the charges. Like, you know, in a way, the gravitational interaction is really has the same fall-off, at least in Newtonian physics, than the electromagnetic repulsion. So there is some sort of cancellation. However, like if you add a cosmological constant, you have a further term, like a further term for the potential that indeed one might think will spoil the equilibrium condition. Basically, anti-de Sitter space behaves like a box, so it pushes the centers together. So it provides an additional, like, attractive force, such that the usual equilibrium condition does not work anymore. At least.
You are aware of these Gibbons-Hawking style solutions. Usually, this multi-center magic happens because there's some underlying integrability.
Mm-hmm.
When you use some good answers, the resulting PDEs are integrable or something. And this, in the subdual case, the integrability is related to twisted theory, but this is not subdual. But do you think you could find some integrable PDEs by choosing some? Okay, to derive even this answer, you must have used some ansatz and plugged them into the Einstein equations to get some resulting simpler PDEs. And presumably those PDEs have some integrability property that you could try to abstract away and generalize. Has anyone tried this for the cosmological constant?
Yeah, I think that people try to do that. It's just that its equations are just complicated. It's not very visible that you have this structure. I mean, in this case, the Einstein's equation, like boiled down to having just the like nabla squared of Laplacian of h equals 0. So it's very easy. Like yes, this equation are just like once you solve this, then this is done pretty much. It's not like this in ADS space, nor in theories of supergravity. So of course you might not expect to find a black hole solution with supersymmetry, because supersymmetry add you another requirement. But you would expect to find these sort of solutions, like for instance, like without requiring supersymmetry, you might expect to find a solution, because overall, if you switch on a very tiny cosmological constant at infinity, you might think that at least for distances, if you place the xi kind of close together, like the bound state will not feel immediately, will not feel like right away. On distances very short with respect to cosmological scale, they will not feel the gravitational interaction, like the potential that appears towards the boundary. So you might think that in general one would be able to maybe modify the charge and the mass, like to kind of modify this condition for the bound state to accommodate for cosmological constant. So this is the general law. It might be possible, but so far the solutions have not been found.
So like just replacing mod x minus xi with a geodesic distance in some ADS space, that kind of simple answers doesn't work.
Yeah, no. I mean, it's not, it's not easy. And I mean, people did not, haven't found them yet. And so this provides a long-standing challenge, let's say, for these solutions. However, it will be nice to find at least some examples, or at least to find maybe some approximate solutions, so on and so forth. Because first of all, now we have the developments about microstate counting. So we would like to see, well, it depends. If this solution produces supersymmetry, there is, let's say, there is hope to find some hints for them from the superconformal index and from the twisted index, so from all the computation I showed you yesterday. So it would be nice to see whether they show up there. And on the other hand, in flat space, this configuration, you have analytic configurations for solutions at 0 temperature. But people, by means of probe actions, also show that this configuration can be there also at finite temperature if you have a very small temperature, though. And solutions for the analytic high temperatures, for the analytic non-zero temperature solutions are not really available. But if you do something with, like, if you carefully analyze the probe action, like Frederick and collaborators, really show that indeed they persist at finite temperature. So in any case, configurations then at finite temperature, if they persist also in anti-de Sitter space, can be used to model something. And so the proposal that I will not I will not focus my lecture on, but I think it's pretty, let's say, exciting to think about it. And it's so Frederick and also Dionysius Aninos and Tarek Anus. Let me just these gentlemen then have proposed that multi-center black holes in anti-de Sitter, so multi-center in EDS would describe glassy systems. So their system, let me see if I need it correctly. Yes, so for them, basically, they think that indeed, so glass is a supercooled liquid, so it's not described by equilibrium quantum mechanics in general. And if you see, like, pretty much a black hole like horizon, I don't know if you've heard of this membrane paradigm and so on, it behaves really like a liquid. So according to these guys, they say that, okay, like, why not, like a black hole indeed behaves like a fluid if it's a single center, but once you lower the temperature, then you might indeed get, and what they got also in their computation, that a single center black hole, so like a single, like say, black hole which has just one connected horizon, this is a dominant phase at a big temperature, like a T large, can actually undergo some sort of light transition with a state in which you have multiple centers. So for T. So this is not entirely so. I'm just tracking the endpoint of this process, meaning that this is the initial point, and this is like, so these centers also, they can be of different size. They do not need to lie on a lattice, so they can be really like in a disordered state. So as I said, I'm just tracking the endpoint of this process because you know that in under general assumption in GR, there is a no bifurcation theorem. So this process is not quite allowed, like classically. In order for allow to a horizon to bifurcate, you have to supplement it by some other like quantum processes. But just to, like as the endpoint, if you just compute it classically, just what is the free energy of this thing and what is the free energy of this, you see that if you lower the temperature, this is favored. So why there is this analogy? So of course you have these black holes in anti-de Sitter. They will model something in the dual field theory, and these people indeed like propose the fact that they will model glassy system because indeed this will correspond to the liquid phase because black hole behaves like a liquid, and then it can supercool, like when you lower the temperature really fast, it can go into a phase like this, which is can exhibit disorder, meaning that, as I said, the centers do not really need to lie on a lattice, so they can be placed. Like if you tune particularly the charges and you place them in a particular way, the system is rigid, and moreover, it is it is disordered as a liquid and rigid as a solid. So this is something, a characteristics of glass. Moreover, a configuration like this can exhibit a very vast landscape, and glassy phase of matter, indeed, they are like systems which are only metastable, which are characterized by an exponential number of local minima. So glassy systems, they will never, let's say, find their own equilibrium, like equilibrium phase, because the system will just scan the entire landscape of all these metastable minima. So you can find also configuration of metastable. You can think of finding configuration also with metastable black holes, like with many, many black holes, with disorder and so on and so forth, and this should describe indeed some sort of glassy systems. Moreover, the last thing is that a configuration maybe I did not focus too much on this in the lectures, but for an anti-de Sitter black hole, like there are techniques for which you can compute, for instance, the viscosity of the. There are techniques for which you can compute the transport coefficients of your system, like from the gravity solution. The transport systems, such as the viscosity, the conductivity, and so on, of your dual field theory system, and a configuration like this, since you have multiple like magnetic moments and charges and so on and so forth, you would expect that a configuration like this will give rise to high viscosity in the dual field theory. And also glass is a highly viscous liquid. It's very, very, like it's almost like a solid, not quite, but it's characterized by a huge viscosity. So there are all these observations made together that indeed will make us think that if you find this sort of configuration, then we may be able to model glass in the dual field theory. Something probably far-fetched, but I think it's also something very interesting to think about. So, yeah.
Could you expand a bit on how exactly black hole behave like liquids?
It's just that if you compute the Einstein's equation on the horizon, in particular limit of large wavelength, you find the Euler equation for a perfect fluid. Like in a nutshell, yes. So you can bend the horizon and like the equations, the equation that are found by like on the horizon, let's say, it's really like you're the one of a perfect fluid. So okay, this gives you a bit of motivation. Of course, it's, as I was saying, it's kind of a bit of it's some sort of like probably not. We don't have so much maybe evidence for this, but it's still something very, very nice to think about that motivates us towards try to find these solutions in theories like which have ADS4 vacuum or ADS4 in general. We just stick to 4 dimensions. So what is the current status? So people have tried to find this. There are some people have tried to find at least this configuration of multi-center black holes. What is the status? The status now. There have been some attempts to finding composite configuration. Let's see, composite black holes I put it ADS4. So I'm just going to give you some references. So there are. So people try to find some black holes which are hovering black holes. So there is a solution with a black hole which stays in equilibrium on top of a black brane, so on top of another horizon which is non-compact. And this was found like by, what is that? Let's say by Nabil Iqbal, Horowitz, Santos. And also at some point, I also, like my paper in 2018, I also did something like we also found them. So these are just configurations, but this I think is still in the probe analysis. But so people have tried to find this. Also, they have found some dynamical, so a time-dependent solution in spaces with negative cosmological constant. However, these are also, you also have some singularities in the boundaries, so they're also pathological. And also, we have also some approximate perturbative solutions. And this paper was very recent. It appeared, I think, a month ago, so on and so forth. But also here, people try to solve the BPS equations with the 1/4, imposing 1/4 BPS, like Killing spinor that preserve 1/4 of supersymmetries. But they also use naked singularities. So they use the solution in ADS with m equals like absolute value of q. These are 1/2 BPS, but they are naked singularities. And the total configuration that they found preserve 1/4. So it's a new step towards solving the SUSY equations for multiple center, but they're also, again, the solution rotate, and they also have naked singularity. So not quite what we want, but people started looking into that. There are some people who look into that, but somehow partial success, not quite what we wanted. So, so for these solutions, it is good, since we are not able to solve the full SUSY equations or the Einstein's equation exactly, we will resort to the probe analysis. So I'm going to explain some of the results that we obtained. So some results are in my paper with Ruben Monten. It was based also on some previous work by, again, the people that I mentioned there, like Anus, Aninos, and the others that found it also before. So we will resort to the probe approximation. So in this way, we are going to do something like this. Instead of focusing on a configuration like this, in which all the centers are of comparable size, we will impose that one center is very big. So this will be a black hole. Okay, this is very bad. Like a spherical black hole. And then we are going to put some black hole of negligible, or let's say, of mass, which is, let's say, much smaller than the first one. And then we're going to see if a configuration of this kind, if this small black hole, this is a probe, can be stable in a background of fixed, like where we fix the metric of the big black hole, and we do not include the back reaction of this black hole on top of this. So we just consider the fact that this is a rigid background, and this is just a particle of negligible mass. And we're going to see if can be stable, can stay here, or it just, for thermodynamics reason or for dynamical reason, this thing has to fall inside the black hole. So we will find that an effective potential, and the probe is given, for instance, by wrapped branes. Wrapped, so M branes, or also D branes. And we will see that So you will have an effective potential. So if the effective potential dips below 0, then it means that the probe can be stable outside the black hole. Otherwise, if the potential just goes like this, is monotonic, then it means that the solution is unstable. Okay, so this is like, you do this when you know, like in the limit in which indeed one black hole is big, the other one is small, and then you might hope that once you make this black hole bigger and you include back reaction, then a configuration of this will become more like something like where the centers are of comparable, like one center is big and the other one gets a bit bigger, so on and so forth, and by adding multiple ones, you'll get to a configuration of that. So, okay, so in these two papers, so I will explain a bit how we did it with our, let me see what time is, okay, we still have time. But, so basically what we did, and we did this in theories of supergravity with embedding in M theory. So then we could indeed like use the probe action for brains, which are wrapped inside internal dimensions, and see if these black holes are stable. So first of all, what we did is that we have set up, like we have started our analysis by choosing a specific supergravity truncation. So, okay, let me just right here. So we have first constructed the black hole in the middle, like this one. So in theories, again, of n equals 2 gauge supergravity. So also the initial solution by Frederick were found in theories of n equals 2 ungauged supergravity. So we are going to keep the same model, just adding the gauging, like because we want an ADS potential at infinity. So a negative cosmological constant at infinity, which means that we have to allow for a scalar potential. So first of all, we have constructed the background. So we'll be in ADS4. So this is the big one. So this black hole comes from the equation of motion of like n equals 2 gauge supergravity. Okay, I'm going to spare you the details, but this is n equals 2 gauge supergravity coming from a particular supergravity truncation, which is from M theory on a specific Sadaki-Einstein manifold. So it's a 7D manifold, which is Q111. So it's a 7-dimensional manifold which has non-contractible cycles. So this is a bit different than the sphere, but it's still like it's very symmetric manifold, but it has non-contractible cycles on which the D-brane can actually wrap. So you have like a theory of gauge supergravity, which is similar to the ones that I've mentioned yesterday. That comes from the 7 sphere. The only difference is that now we have like one hypermultiplet as well. So we have to include this matter content, because that's also what you get from that's really what you get from the reduction of 11-dimensional supergravity on like doing a consistent truncation. So the matter content is one vector multiplet. So one hypermultiplet, 3 vector multiplet. And of course the gravity. And indeed, so in the Lagrangian, which is indeed, as I'm not going to write it down again, I write it so many times, but yeah, like you have, of course, the Einstein-Hilbert term, plus the Einstein-Maxwell term, which is also coupled with the imaginary part of n and the sigma, plus all sorts of things. So it has all the couplings of the supergravity Lagrangian, of course a potential, which indeed depends on the vector multiplet scalars and the hypermultiplets, but also like it has some, like it has the hypermultiplet coupling, like the kinetic term, which include a covariant derivative. So it means that the hypermultiplets are charged with respect to the gauge group. This is something peculiar to this truncation, and in general, gauge supergravity with this abelian gauging, for this kind of theories, you have that the hypermultiplets are charged. So this means that indeed they will have like vector fields, so the covariant derivative will be supplemented by having this, like the killing vectors. Like, okay, this is like it's related to the supergravity Lagrange, but in general, they will have like a linear combination of the gauge field, which is indeed appears in the supercovariant derivative. Sorry. So this means that given the fact that you have a non-vanishing covariant, like the gauging is in such a way that you get something in the super, like you get this linear combination in the covariant derivative. This materializes in the fact that indeed one linear combination of the gauge field is massive. And in this case, we parameterize it in this way. So this linear combination is. So we're going to have a massive vector field in our spectrum. This is also something that really indeed exists in our spectrum, even in the vacuum. So we need to solve our equations of motion for this. We solve the equations of motion because we really wanted to see that when you lower the temperature, so you start from a high temperature, and then when you step down to lower temperature, you want to see that states with probes which are stable outside the horizon get populated. So that's why you want to start. You don't want to solve the SUSY variation, but you want to solve the Einstein's equation in order to be able to tune the temperature. So we did this. So you need to compute the Einstein's equation for this. You set up, so since the scalars are charged, so this way here, sorry, mu I. And so since the scalars are charged, this means that your system is very complicated. Therefore, you need to resort to numerical techniques. So we solve for the background numerically. And indeed, you find the solution. You have to be a bit careful with the boundary condition, but in general, you find a black hole solution with all the warp factors. So we impose the static and spherically symmetric ansatz. So if you choose a metric of this form here, it's already, you will be very, well, it's slightly different than what we chosen before, but it's just a different reparameterization. So with a static and spherical symmetric ansatz, plus the fact that the fields depend on R, and the gauge field has this sort of ansatz here. So we solve our equation for this static ansatz. And we solve them numerically. So we get a full configuration of black holes. So you are going to have, like the computer, indeed, you can plot the various warp factors, but you can also plot, for instance, the behavior of the matter field. And so for this sort of black hole, so this black hole turns out to be surrounded by this massive vector field that I showed you, that I told you at least that there is indeed one linear combination which is Higgs. So this black hole will be a black hole that we called it like black hole with halo, because in general you have a black hole. So the profile of the massive vector, which we call psi, in function of r, so r minus, we set r equals 0 to be our horizon. So it will be 0 at the horizon, and then it will be peaked, and then it goes to 0 after. So a specific location. So if you plot the black hole well, in coordinate system that I'm not going to specify now, but all around you have this halo, let's say. So you can look at picture, for instance, in my paper, the last paper with Ruben is figure 1. It's a very nice, I cannot really show you now, but it's kind of a nice color picture. You'll see the gradient. We color it in different way, but the halo is peaked at a specific radial coordinate. So this coordinate here is really the peak of the halo. And we will see that this will have some consequences for the probes. So we will see that the probes actually like to stay stable, just really on top of around the area where the massive vector is also peaked. But okay, so we have found this configuration. So we have studied also the thermodynamics of the solution because you have temperature. So we have verified that our solution satisfies the first law of thermodynamics.
Sorry.
Yes? Sorry, yeah.
What's the halo? Can you just...
Yeah, so like the halo would be, so we have a black hole and it's supported by matter, supported by scalar fields, vector fields, and so on. And in general, when you have massless vector field, this is the normal supergravity black hole that you find in general. But this guy has also this vector field here, this massive vector field, which is non-trivial. It's turned on, and it's broken. Like the symmetry is broken also all the way to the vacuum. So it's really like a massive vector in your spectrum. It's different than the one that people have found before, where, for instance, the symmetry is broken just near the horizon. But it's basically the fact that you have a black hole and some massive object, which is the massive vector field, which has this profile around the black hole. So outside the black hole, you have a profile which is very peaked at a specific coordinate outside. So that we call it the halo.
Oh, okay.
And so it satisfies, so our black hole satisfies also the laws of thermodynamics, lambda. And so indeed, we have used this thing to kind of check the accuracy of our numeric solution because indeed we don't have it analytically, we have only numerical solution. And also we have also managed to, so also given the fact that this configuration is charged, you also have the sort of behavior temperature versus area that we had before. So we avoided the unstable branch. So in order to put probes only on the stable configuration, you remember that we have seen this in the first class. We have seen that we have to avoid some of the branches because they are unstable. So we just put probes on the other two. Actually, we avoided the phase transition. So also this we didn't put, and also here. So we just put it here, yes, and also here, yes. So for these configurations, once you know the metric in 4D, you can readily, so you know that this configuration in 4D will automatically solve the equations of motion in 11D. And you know the uplift formulae, so you know exactly what is the metric, for instance, in 11 dimensions. And let me see, I can just skip that. But so once you know the metric in 11 dimensions, then you can use the probe action for instance, for various sort of brains, M brains, for instance, and check whether this, like the potential that you get from this probe action tells you that the brains are stable or not. So the action for the brain will be of the form, for instance, this is the M2, will be of this kind. Where this is the pullback of the matrix of the M-brain like metric, and this is the integration over the tree form in M theory. So if you plot the effective potential coming from this, so you have that for M2 brains, you don't have any inflection point. So this thing starts to 0 at the horizon and then goes just monotonically. Somehow you don't find stable probes when you consider M2. It's also true that we actually, in the probe action, we only use the solution with only one kind of charge. So putting the probes which are of the same nature on a background, indeed is something that we would expect that we would not find stable probes actually, because you need charges of different nature to form a bound state. This comes from the intuition that we have in flat space. So we somehow expected, but just by putting M2 branes, we would not have found stable probes. However, we needed some more, let's say, some probe with charges which are indeed more like with a variety of charges, in particular charges that are mutually non-local with respect to the one that you have in the background. So for instance, we consider other kind of probes, which are the D6 with word volume flux along, so we reduced, our theory lives in 11D, we reduced it to type 2A, and then we put the D6 branes on the 6-dimensional manifold which is obtained upon reduction from 11D. So we put also some word volume flux on the D6 brane, and we see that indeed we managed to find stable probes. So the effective potential in function of the radius really behaves like this. So you have that when you, this is for high T, then when you lower the temperature, it gets like this. So it comes to an intermediate step in which, indeed, the probe is metastable. So, yeah. I mean, this thing is like T. Yeah. So this is unstable. This is metastable. And this is stable. So indeed, it seems that when we lower the temperature, like enough, for a specific, we have to really search for the parameter space. You have to, I mean, we took some intuition from the results that Frederick and his collaborator had, and we had to really search very carefully scan the parameter space. But basically, what we have found is that for a specific kind of smallish like range of parameters, we have that a flux D6 brane, if you wrap this brane inside internal dimensions, can indeed give a potential which has a global minima outside the horizon. So it means that if you have a background black hole, which is the one with the massive, with the vector field halo, and you put a D6 brane like here, like at this point, this will stay outside, will not fall inside the black hole. So you have to really make sure that this one also has the correct charge. So a brane with the correct charge in this sort of background with this temperature will stay outside the black hole. So from our analysis also we could draw the following conclusions. Okay, maybe it's better to put it here. So the conclusion that we draw is that our black hole background is surrounded by this sort of like atmosphere, like this sort of massive halo, which is peaked outside the horizon. And we have noticed that a lot of our stable probes are actually like become indeed at the peak of the vector field halo. So it means that somehow if we plot the radial component for the probe potential, it seems that they sit around here. So it means that outside this black hole in anti-sitter, which is supported by lots of matter and so on, there is some sort of basin of attraction in which all the massive objects tend to stay in a stable way. And this was something that I think was a bit new. That I don't know if we could have expected that, but it was a bit of a surprise.
Can I ask you a very basic question? Why do you have to go to type 2A instead of using some KK magnetic monopole in 11D?
Oh yeah, we could do that. Just that it was like very hard to use that.
Okay, so just a dumb technical reason.
Yes. So we just reduced to 10D, and we knew exactly where to put the D6 brane, and then it was easier this way. So yes, this is like I'm sure that some other people who are more skilled in DBI action or brane action would have probably done it more skillfully, but yeah, we just decided to do this way. And so indeed, the stable probes, they kind of stay like around the black hole. So if you see, there's also like the picture that we put in the introduction is kind of very, very suggestive. So if you want to look at the paper, I think it's kind of nice. And so the paper doing some sort of small self-advertisement, is this one, 2011, 06, 879. So the probes, well, we have shown different kind of probe configuration. We have seen that, so these are the stable probes in general, they stay kind of on top of the black hole halo. The metastable one instead get pushed a bit towards the center. So they're metastable one, they stay around here. And moreover, we have also noticed that if you increase the size of your black hole, the probes get also pushed a bit like towards the horizon a bit more. And this is because your black hole fills up the spacetime. So the probe starts feeling like earlier the potential of ADS. So this is something that is still compatible with the physics. So we have also tried to do this sort of analysis with BPS configurations. So there are solutions of black holes, like the black hole in the center. We have found it via the Ansatz equation. So in our solutions, you have some temperature for this black hole, but you can also try to tune the temperature really close to 0 and to insert the BPS values for the charges. So BPS solutions were found by some other people, by Halmagyi, Petrini, and Zaffaroni. So with our techniques, we managed to get really, really like close to the BPS solution. And however, we have seen that, so this probe arises only for configurations which actually have a t equals 0 limit, which is non-supersymmetric. If you impose a supersymmetric configuration, somehow the probes, stable probes are not there. You get a graph like this. So it would seem that from our analysis, for which we really we only choose one kind of charge. I mean, it's a really reduced analysis, but for our configuration, it seems that you don't have bound states which are BPS. With a caveat, but it seems that for us, we don't find those.
Do you have any physical interpretation of what is the case? So some radiation emission or something that stabilizes. I mean, why? Surely
Yeah.
I don't know, maybe the opposite.
Usually, yes, usually it's the opposite. I think that there exists also this multi-center configuration that do not preserve supersymmetry, even in flat space. But for me, I think that in this case, it's just because we scan a very, very small. So it could be that because we also, in our setup, we set to 0 some of the matter content. Like we have truncated our setup to really the minimum matter content, because the matter content is it's 1 hypermultiplet, 3 vector multiplets, and a gravity multiplet. It's a lot of fields. We had 14 equations to solve, so it's it's very demanding for the computer and so on. So we had to reduce it to the minimum. So we have really we have thrown away a lot of matter that could give some more physics. So for the moment, I would say that we cannot rule out supersymmetric configurations. For some reason, we don't find. But okay, in the last, maybe I can go maybe 10 more minutes. And and by the way, so first of all, let me just mention that for this sort of configuration, this M theory on this Q11, so the dual field theory is similar to a BGM. It's another three-dimensional superconformal Chern-Simons with some matter in the adjoint. But the microstate counting for the single center configurations is problematic. So there is still some work to do for the single center. So it's still very early to see whether we can find some evidence for this in the dual field theory by computing the index. So this is something that, and even for a BGM, where people have computed the twisted index and the superconformal index, computations did not show existence of multicenter black holes. So for the moment, it seems that somehow from the index, people have not seen multicenter black holes, but you never know. It's really at an early stage. But just that we have seen that with our computation and with the computation of Frederick, at least we have seen that in the probe analysis, where you find a big black hole and a small black hole, it seems that even in anti-de Sitter, you can find this solution. So it's a good sign. Whether they preserve supersymmetry or not, we are not sure, but in principle, this is a proof of principle that this solution should be there. Okay, then let me, in the remaining 5 or 10 minutes, I will tell you like something about black rings and black Saturns in anti-de Sitter, why we expect them or why we don't expect them, whether they preserve supersymmetry or not, or yes. So as I was mentioning, in higher dimension, like higher dimensional gravity really allows for black holes of different topologies. For instance, rings.
Sorry, can I ask you a question?
Yes.
The effective potential, like how do you compute the effective potential?
From the dBi action for the probe. Like it's really from the action of a probe which sits in a background which is rigid and given by your black hole background. So yeah, in general you decide like a value for the flux for this D6 probe, and then you insert all the quantities relative to the rigid background in the dBi action. And indeed, actually the probe action that you get from the dBi for this flux D6 brane, which wraps each time around each sphere once, it's very easy because action that you will get from here, you get something like this, and I can just write it down. Where this m gamma is actually the central charge. Well, okay, here you can see that it's the, wait a moment, sorry. This is just a generalization of the electromagnetic force, and this is like the mass term that you get from the dBi action, so which is the first term which concerns the determinant of the pullback of the metric and so on, can be rewritten in terms of the quantity that yesterday I called the central charge. So it's kind of very similar. Actually, if you do the probe also in flat space, you get that somehow, you get a similar formula. Well, actually, you get, in this case, yes, the same formula. Of course, we have made some assumption of our background, but it's, and also, this formula here was also found by Frederick in the context of D6 branes on S7, so something that probably we would have expected, but it's a very simple formula. It has a mass term and electromagnetic term, and you see that when these two conspire, you can have a minimum. Okay, in the last 5 minutes, let me just tell you why we don't expect supersymmetric black Saturn in.
You said it. One trivial thing. How do you wrap the D6 on your 7-dimensional Sasaki set? So you have some cycles that you wrap.
Yeah. So basically, once you reduce this Q1-on-1 is made pretty. It's a U1 fibration over 3 2 spheres.
So you're taking on the 3 2 spheres.
Yes.
Okay.
That's why it was also easy for us to because once you get upon reduction, it's just 3 2 sphere and you wrap it around. And yeah, so that is our configuration. What we have done. Okay, I have 5 minutes, but yeah, just to give you an idea. So we can find in 5-dimensional black hole solutions. So in flat space. So there are black rings. With something that pictorially looks like this, and also black Saturns. So there are black holes surrounded by a black ring. And also you can have even, for instance, you can have concentric black rings, so something like this, and then maybe some other ring that's spinning to the other direction, one on top of the other one in the center of the, concentric, meaning that they share one center, or even you can have multiple rings, let's say like this, or maybe one like this, for instance, and one black hole in the center. So you have multiple configurations of this kind. You see that before we had a point-like particle on top of a spherical black hole. In 5D, you can also have like a continuous distribution of matter. So these are also like black holes, which indeed they have something like, they coexist due to the mutual repulsion between the center, for instance, and the ring. The ring usually spins, so it's the angular momentum that makes the ring kind of stay stably and stay in equilibrium. So they preserve, so these solutions in flat space, you can find them, both BPS and non-BPS, with charge or without charge and so on. Many people study these configurations, like to name a few, Roberto Emparan, Javier Real, then also Jerome Gauntlet, Joseph Bena, Nick Warner, many of them. So can this solution exist in asymptotically ADS space? So we have different equilibrium conditions. And it turns out that these solutions, when you don't insist on preserving supersymmetry, these solutions have been found. So they have been found, neutral black rings have been found, both in the probe approximation and by back-reacting geometry, so exact. And also black Saturn, they were found, first with a Schwarzschild black hole in the center, but also with my collaborator, that's work in progress, but we have found a configuration like this with a rotating black hole in the center, so with something with J non-zero. When you have supersymmetry, when you have supersymmetry in flat space, do you expect supersymmetry to still be preserved in asymptotically ADS? Well, a computation of Emparan and collaborators indeed shows that this is not possible. And these computations were found in the probe approximation, meaning that they try to, so via the Blackfold equations, which are again the equation that describe the fluid living on the horizon, let's say, people try to bend a supersymmetric black string, so something like this, to bend a thin black string in a ring, so to close pretty much, to take this configuration, supersymmetric black string, and then put it in ADS space and just close it like this. And then they saw that this is indeed not possible due to the Blackfold equation, so in this way. So this object here, supersymmetric black string in flat space, is characterized by the following stress energy tensor. It's okay, I'm skipping a lot of details. I mean, in particular, the string is is parameterized by the coordinate like t and z. Okay, I skipped a lot of, but I think we are kind of late, but just to give you the gist of how the computation is. And the equilibrium, so first of all, so this is the stress energy tensor that would give rise, so that will give rise as let's say, this is just the stress energy tensor which is sourced by a supersymmetric black string. We want to see the Blackfold condition gives you some, the Blackfold equations give you some condition for this, for a configuration of this kind to be stable in a background, for instance, of a black hole or anticipator space. And the equilibrium condition that you get from the Blackfold equation is basically this. So if you find a solution for this equation here with real and positive R, it means that your solution can be stable in ADS space. So this is the equilibrium condition that you have for ADS space, where you see that ADS space with the ADS length L. So the stress energy tensor of the source that you put in ADS space should satisfy this condition to be stable. But you see that if you plug in the stress energy tensor for a supersymmetric black string, you have to, this is non-zero, but this is zero. So this term here So I'm just parameterizing the string with time, and this is z is the coordinate along the string. So basically this term here goes to 0, but for ADS space, this is non-zero, and this is also non-zero. So you cannot balance, you're not able to balance the, let's say that the black string does not have the sufficient pressure to be able to stay like in ADS space and in equilibrium. It will just collapse on itself. You see that for ADS, for flat space, you send L to infinity, means that this term goes to 0, so this equation is satisfied. But in anti-de Sitter, you cannot balance the two forces. So we don't expect, at least from this kind of considerations, we don't expect to have supersymmetric black rings in anti-de Sitter space. We also generalize, we have computed the stress energy tensor for black strings also with scalars, with further charge and so on, and it looks like it's the same. We cannot really get these equations to work. So somehow that is a bit of that is something that will hint to the fact that perhaps rings with SUSY are not possible, and we don't know if probably like adding a black hole in the center and making it spin most likely will also not turn out to be supersymmetric. I mean, most likely the attraction from the black hole will also make the ring shrink even more, but it's something that is under consideration. So we are still working on that to see if you can put a supersymmetric black string, you make the black hole supersymmetric and you make it spin, perhaps it can balance the collapsing of the string. But this is something that, yes, we still need to see. And just one caveat, that this black string is actually 1/2 BPS, so in the language of like 10D or so on, this is a 1/8 BPS black string. But we see that, for instance, the Gutowski-Real black hole, the supersymmetry that you have in anti-de Sitter, well, this would be like 1/2 BPS. But you see that the supersymmetry that you have in anti-de Sitter is 1/4, so it would correspond to 1/16 BPS. So could be that other configurations of black ring which are not directly connected to the flat one exist, which preserve maybe less supersymmetry, but for now we don't know yet. So just that, let's say, transposing the same reasoning that you have in asymptotically flat to anti-de Sitter will make you think that configurations like this might not be SUSY in ADS, and therefore will also not show up in the computation of all these superconformal indices. So okay, I think that I'm finished.
Okay. So I suggest we postpone the questions for the discussion session, and let's thank Chiara for this nice set of lectures. So we resume at